Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries. We have another hard one for you today. It is day 16 of our hashtag 30 Days of Code Challenge with Educative. This question is called Find Longest Self-Contained String. Let's get into it.
Today's problem is one of the most deceptively hard ones you'll encounter. Find the longest self-contained substring. This problem is a perfect example of how reframing, not brute forcing, is the real skill behind solving hard problems. Once you see the right structure, what looks impossible becomes almost simple. We're given a string S and we need to find the longest substring where every character inside that substring exists only inside that substring, nowhere else in the entire string. Let me make that concrete with an example. If we take the string A, B, C, A, the substring B, C is self-contained. Why? Because both B and C appear only inside that window. If you look at the entire string A, B, C, A, the letter B appears exactly once at index 1. The letter C appears exactly once at index 2. So the substring BC is valid. But if you try the substring AB, that's not self-contained. Why? Because the letter A shows up again at index 3, outside the AB window. So any occurrence of a character outside your chosen substring disqualifies it. Our job is to return the length of the longest valid substring, or return -1 if no valid substring exists. This definition is strict on purpose. It forces you to think globally about where characters appear across the entire string, not just locally within a window. Let's warm up with a concrete example so you can see this in action. Take the string ABAC. Let's check some substrings. First, try ABA. That covers indices 0, 1, and 2. The characters inside are A, B, and A. Now, does every character in ABA appear only within that window? Let's check. The letter B appears only at index 1, so that's fine. But the letter A appears at indices 0, 2, and also at index 3. Index 3 is outside of the ABA window, so ABA is not self-contained. What about just the letter B at index 1? Does B appear anywhere else in ABAC? No, it appears only once. So B is a valid self-contained substring of length 1. Similarly, the letter C at index 3 appears only once, so C is also a valid self-contained substring of length 1. So the answer for ABAC is 1, the length of B or C. This tells us something important. Single character substrings can be valid, but only if that character doesn't appear anywhere else in the string. To solve this efficiently, you need one fundamental mental shift. Stop thinking locally and start thinking globally. Here's the key concept. For every character in the string, we compute what I'll call its interval. This interval captures where that character lives across the entire string. For a character C, the interval is defined as first of C, the first index where C appears, last of C, the last index where C appears. The interval is the range from first of C to last of C, written as first of C, last of C. Let me show you what this looks like for our example A, B, A, C. The letter A appears at indices 0 and 2, so the interval for A is 0, 2. The letter B appears only at index 1, so the interval for B is 1, 1. And the letter C appears only at index 3, so the interval for C is 3, 3. Once you visualize characters as intervals on a number line, the whole problem opens up. You're no longer asking which substrings work, You're asking which intervals fit completely inside which regions. Here's the critical realization that makes this problem solvable. A substring from index L to index R is self-contained if and only if every character that touches the substring has its entire interval inside the range L, R. Let me unpack that. If your substring L, R contains the letter A, then the interval for A, which is first of A, last of A, must be completely contained within L, R. If the interval for A extends even one index beyond R or before L, the substring is invalid. This transforms the problem from a substring problem into an interval containment problem. Instead of checking every possible substring and verifying characters one by one, we check which merged blocks of character intervals to find valid self-contained regions. This is the reframing that turns a brute force nightmare into a crisp, structured solution. Let's talk about why the brute force approach collapses. The naive method would be try every possible substring, and for every substring, verify that all characters inside it stay completely inside that range. Here's what that looks like in terms of complexity. First, there are roughly n squared possible substrings in a string of length n. Every starting index L combined with every ending index R greater than or equal to L. Second, for each substring, you need to check whether every character inside it appears only within that substring. In the worst case, that's another O of n scan for the entire string. So you end up with O of n squared substrings times O of n verification per substring, which equals O of n cubed. For a string of length 1000, that's a billion operations, and that's way too slow. Hard problems are usually about escaping cubic or quadratic time by finding structure that lets you skip redundant work. Step 1 of the optimized solution is straightforward and fast. Scan the string from left to right. For each character, record the first time you see it and the last time you see it. Let's walk through A, B, A, C, D as an example. At index 0, we see A. This is the first time seeing A, so first of A equals 0 and last of A equals 0 so far. At index 1, we see B. The first time seeing B, so first of B equals 1 and last of B equals 1. At index 2, we see A again. We already know first of A equals 0, so we just update last of A to 2. Now the interval for A is 0, 2. At index 3, we see C, first time, so first of C equals 3 and last of C equals 3. The interval is 3, 3. At index 4, we see D. This is the first time as well for D, so first of D equals 4 and last of D equals 4. The interval is 4, 4. This takes O of n time, just one pass through the string, and now each character is represented as a segment on a number line. Now, we have a list of character intervals. The next step is to sort them by starting index and merge any overlapping intervals. Why do we do this? Because overlapping intervals form natural blocks where characters interact with each other. These blocks are the only candidate regions that could potentially be self-contained substrings. The merge rule is simple. Start with the first interval. For each subsequent interval, check if it overlaps with the current block. If the next interval starts before or at the current block's end, they overlap, so extend the current block to include it. Otherwise, the next interval doesn't overlap, so close the current block and start a new one. This is the classic merge intervals pattern you've probably seen before. Let's apply this to A, B, A, C, D to see it in action. The intervals we computed were A is 0, 2, B is 1, 1, C is 3, 3, and D is 4, 4. First, sort them by starting index. They're already sorted in this case. So just as I stated, that's the sorted order. Now, merge. Start with 0, 2. That is our current block. Next interval is 1, 1. Does it overlap? Yes, because 1 is less than or equal to 2. So we merge it into the current block. The merged block is 0, max of 2 and 1, which is still 0, 2. The next interval is 3, 3. Does it overlap? No, because 3 is greater than 2. So we close the current block, which is 0, 2, and start a new block, which is 3, 3. The next interval is 4, 4. Does it overlap with 3, 3? No, because 4 is greater than 3. So we close 3, 3, and start a new block, 4, 4. The final merged blocks are 0, 2, 3, 3, and 4, 4. Each of these blocks is a candidate region that might be self-contained. Now comes the critical validation step. Just because we've merged intervals doesn't mean every merged block is automatically valid. We need to check. A merged block from index L to index R is self-contained if and only if for every character in the entire original string, if that character's interval intersects the block L, R at all, then the entire interval must be contained within L, R. Let me say that again more carefully. So for each character in the alphabet that appears in the string, check its interval. If the interval is completely outside L, R, that's fine, no problem. If the interval intersects L, R even partially, then the entire interval must fit inside L, R. If it sticks out to the left or right, the block is invalid. This is the validation rule that determines whether a merged block is truly self-contained. Let me show you an example where a merged block fails validation. Take the string ABCAB. First, compute character intervals. The letter A appears at indices 0 and 3, so the interval is 0, 3. The letter B appears at indices 1 and 4, so the interval is 1, 4. The letter C appears only at index 2, so the interval is 2, 2. Now, after sorting and merging, you might get a block like 0, 2. Does this block contain all necessary intervals? Let's check it. The block 0, 2 contains characters A, B, and C. Check A. Interval is 0, 3. Does 0, 3 fit inside 0, 2? No, it extends to index 3, which is outside the block, so this is invalid. Check B, which is interval is 1, 4. Does 1, 4 fit inside 0, 2? No, it extends to index 4, which is outside the block, and that also is invalid. So the block 0, 2 fails validation. It's not self-contained because characters inside it have parts of their intervals extending beyond the block. Now let's look at a valid example. Go back to the example that we had that was ABACD. We've computed merged blocks, which is 0, 2, 3, 3, and 4, 4. Let's validate the block 0, 2. What characters are inside 0, 2? Looking at the string ABACD, indices 0, 1, 2 contain ABA. So the characters are A and B. Check A. The interval here is 0, 2. Does 0, 2 fit inside 0, 2? Yes, perfectly, so this is valid. Check B. The interval here is 1, 1. Does 1, 1 fit inside 0, 2? Yes, so that's also valid. So the block 0, 2 passes validation. It's a self-contained substring of length 3. Similarly, blocks 3, 3 and 4, 4 are single character blocks, and they're also valid because those characters appear only once. The longest valid block is 0, 2, which has a length 3. That's the answer. Let me summarize the full algorithm and its complexity. Step 1. Build character intervals. Scan the string once, which is O of n time. Step 2. Sort intervals by starting index. If there are k distinct characters, that's O of k log k time. Step 3. Merge overlapping intervals. One pass through the sorted list, which is O of k time. Step 4. Validate each merged block. For each block, check all k character intervals to see if they're contained. In the worst case, this is O of k times the number of blocks. Since the number of blocks is at most k, this is O of k squared. So the total time complexity here is O of n plus k log k plus k squared. But here's the key insight. K is bounded by the size of the alphabet. For lowercase English letters, k is at most 26. So k log k and k squared are both constants. The dominant term here is O of n. The space complexity is O of k for storing the intervals and blocks. This is a massive improvement over the naive O of n cubed approach. Let me put this in perspective. The naive brute force O of n cubed time complexity for a string of length 1000, that's a billion operations. Now the optimized interval approach, which is O of n time complexity, for a string of length 1000, that's 1,000 operations. The difference between a 3-nested loop and a clean interval merge approach is dramatic. This is the kind of operation that separates a failing solution from a passing solution in interviews. And more importantly, this is the kind of thinking that trains your brain to see structure instead of just trying harder with brute force. The key mental shift for this problem is this. Stop asking which substrings are valid. Start asking which merged character interval blocks contain all the necessary character intervals. Hard problems get easier when you stop thinking in substrings and start thinking in structures. Intervals are a structure. Merging reveals the natural boundaries where characters interact. Validation checks whether those boundaries are truly self-contained. This mental model applies to dozens of other problems involving ranges, segments, and containment. Today, you learned several powerful techniques. First, how to convert characters into intervals. This transforms a local substring problem into a global interval problem. Second, how merging intervals reveals natural substring boundaries. Overlapping intervals indicate regions where characters interact. Third, how interval containment defines self-containment. A block is valid if all touching intervals fit inside it. Fourth, why brute force collapses on hard problems. Cubic time does not scale. You need structure. Fifth, why the right framing solves hard problems cleanly. Reframing is often more important than algorithmic tricks. Patterns like this appear again and again in competitive programming and technical interviews. Master the pattern and you unlock dozens of problems.
And that's a wrap for day 16 of our hashtag 30 Days of Code Challenge with Educative. If you like this video, like it down below, share it with a friend. Subscribe to our channel. We would love to have you, and we hope to see you next time.